Here comes more sophisticated version of chaos course. It has a very good mathematical pedigree, and in physics, it was reinvented a couple times by Martin Gutzwiller and then by David Roel. It goes by the name periodic orbit theory. So the earliest example that I can find of it was done by Osorio de Almeida and Hanai, which looked at this time evolution Jacobians, and they announced the principle of uniformity. The idea of principle of uniformity is you are in a busy subway station in New York, let's say Times Square subway station. There are about 10,000 people, they're all moving, and they're all avoiding each other. And that's what unstable orbits do. They're unstable, so if you try to get close to them, they push you away. But they have to be accommodated in a confined space. So that's ergodic theory. You have many humans, cats, etc., and they have to stay away from each other. And they call that principle of uniformity. What will happen is they'll try to get kind of equally distributed within the station, and each one of them will have a label, name, ID, social security number, and it will have its natural weight, which is, how much space does it require in this situation, what size of its neighborhood. They call that natural weight. Little calculation says it should be determinant they just gave you of time evolution matrix going m steps in time. It specifies which one, so this is your social security number, and it has to be periodic because we have translation invariance, and that's the principle of uniformity. And various people, Ruel and Copenhagen group, etc., developed this further. So it's a theory, it works, it's good. Intuition is as you go forward in time, everybody jostles in such a way that state space, possible positions of all people in this Times Square subway station. State space get partitioned in small neighborhoods of individuals, and there are little invisible clouds around them. Now, what does it have to do with Hill determinant? Weird. Well, in periodic orbit theory, the first thing you have to learn is that if you have a number of cats, which is called points in state space, evolution moves them around, but it doesn't kill them. Unlike quantum mechanics, we are very kind to cats, except if you're Russian like Arnold and you slice them. So that's called flow conservation syndrome. So it says that the sum of these neighborhoods has to be invariant in time, and it's conveniently normalized to be 1. So the whole space gets divided. And the relation between time evolution and orbit stability is given by Hill and Poincaré. So indeed, these guys count orbits because they have to add up to 1. And for each one of these exponentially many social security numbers, there is little volume. So they're indeed counting. So that's surprising, but that's how it works. For Bernoulli, this system, it's actually not very helpful. It's a little bit too simple because Bernoulli is democratic. Everybody is stretched by same factor to every place. So stretching is uniform. So all of these determinants that measure stretch are the same. And in that case, if they're all the same, their sum should equal to 1, which means the number of them equals determinant. That's obvious. In general, they're different, each orbit. Fat orbits have bigger neighborhoods than thin orbits and stuff like that. But in this case, it's very democratic. Now, if you remember fundamental fact, period 2, there was a unit hypercube. And now if you look at pre-images from this fundamental orbit Jacobian, and remember, this is encoding of our law, you're nice to your neighbors. It partitions the space into little subspaces. And in this case, each one is 1/3 of the volume. It's labeled by a fixed point. Remember, the thing was producing by a number of fixed points. And it produces correct counting. So that works.